Picture this. You're sitting at a quiet study table, a warm lamp is switched on, casting this nice soft glow over a blank, cream-colored notebook. Beside it, you've got a pencil and a freshly poured cup of chai. The pages are turning slowly. Welcome to our explainer of Ravindra Nayak's incredible work, Book 2, Deep Learning from Second Principles. Now, if you caught the first book in this series, you know we built a really quiet, solid foundation by just asking, what does it actually mean to learn? But today, we're opening that notebook to a much deeper page.
We are moving out of the philosophy of learning and diving straight into the actual machinery. And don't worry, we are absolutely not going to start with a giant wall of code or heavy mathematics. Instead, we're going to look at the inner journey. What literally happens inside a learning system? How does a chaotic, real-life detail enter a machine? And how on earth does that machine adjust itself to become more useful? Let's find out.
All right, let's kick things off with Section 1, the single neuron's decision. To really understand the entire machine, we've got to zoom way in. We need to look at the smallest, meaningful movements inside a deep learning model. So we begin with the single artificial neuron. Now, let's be clear. It is not a biological brain cell. It's not magic either. It is simply a tiny mathematical decision room. But you might be wondering, how does that actually work? If it's just a piece of math, how does it process something from real life? How does it decide what actually matters and what is just background noise?
Well, that is exactly the right question to ask, and it works because it follows a highly organized step-by-step movement. It essentially goes like this. First, information, which we call the input, enters the room. Second, a weight assigns importance to that input. Third, a bias shifts the system's baseline readiness. And fourth, an activation function shapes the final response. I know that sounds like a lot, but let's look at each of these tools closely. Let's start with weights. Think of a weight as the system's learned sense of importance. Imagine you are choosing a route to a very important meeting. Distance matters, sure, and traffic matters too. But if you're already running 10 minutes late, the traffic suddenly matters way more than taking the scenic route, right? A weight is just the system's adjustable way of saying, okay, this particular signal should count this much. It decides which signals influence the outcome heavily and which ones barely matter at all. Next up is bias. Think of bias as the starting lean of a decision. Sometimes a system just needs to begin somewhere before the evidence even fully arrives. It's like a little nudge. You know how some people are naturally optimists and agree easily, while others are cynics who need a massive amount of evidence to change their minds? Bias gives our mathematical system that exact kind of flexible starting point.
And finally, we have activation. Look, a gathered total of evidence by itself is kind of like a thought that hasn't been spoken out loud yet. Activation gives the neuron its voice. Imagine a lantern that is programmed to only turn on when the room gets dark enough. The darkness is the input, but the switch itself decides what to do with that information. Activation is simply the gate that decides if the gathered evidence is strong enough to pass forward.
Now, I know what you're thinking. When you open a typical AI textbook, you are usually greeted by a terrifying wall of math. You see all these symbols, X, W, B, Y, and it feels completely overwhelming. I get it. But notice how simple it is once we organize it. These letters aren't there to intimidate you. They're literally just a filing system for meaning. X is just the input entering. W is the weight changing the influence. B is that starting bias we talked about. And Y is the output response. So the next time you see a formula, just remember, it is nothing more than a compressed story of what we just discussed.
Moving right along, let's look at Section 2, layers building meaning together. Once the single unit makes sense, we can start drawing many of these small decision rooms side by side. We're scaling these single units up into a cooperative structure. We are entering the world of layers. A single neuron all by itself honestly means very little. It's like one small vote in a massive group. But when you have many neurons working side by side in a hidden layer, each tuning into different pieces of evidence, something really beautiful happens. The layer's output isn't just one isolated sound anymore. It becomes a chord of responses. And that chord becomes the input for the very next layer. Meaning gets built stage by stage, reshaping the signals as they travel deeper and deeper into the network. So you can probably picture the information flowing forward now, right? But here is the million-dollar question. What happens when the network gets the answer wrong? How do we actually know which of those thousands of weights to change and exactly by how much?
Which brings us to Section 3, learning from measured mistakes. This is the true turning point, the very heart of the machine. It's how a network actually improves after making an error. We are looking at the mechanics of course correction. Think about human learning for a second. When we make a mistake, it usually carries some emotional weight, doesn't it? It might mean scolding, red marks on a test, or just this quiet feeling of shame. But inside a machine, error is absolutely not an insult. A machine doesn't feel pride or embarrassment. It only has a way to mathematically compare what it produced with what was actually needed. We call this measurement loss. Loss turns a wrong answer from a painful failure into a highly useful, actionable information. Picture this loss as a literal hill. If the loss is high, it is like the model is standing way up high on the peak of a mountain. It made a massive mistake. The entire goal of training is simply to walk down that hill. Low loss is reaching the valley at the bottom, where the mistakes are tiny. The system literally just wants to step downhill to reduce its errors. Stepping downhill makes total sense. But wait, the system is essentially blind, right? So how does it know which way is down? Well, it uses a gradient. Now, the word gradient sounds like some frightening calculus concept, but here's what it actually means in plain English. It is just a directional hint, a guide for movement. It simply tells the system which tiny adjustment to the weights will take it one step lower on that hill of loss. Okay, so the gradient gives the direction for the final output. Easy enough. But what about all those hidden layers in the middle? If the final answer is wrong, how does the network trace the mistake back through all those earlier chords and votes we talked about? That is exactly what backpropagation does. It is this incredibly calm, logical return path of responsibility. Think of it like a whisper passing backward through all those decision rooms. If the final output was wrong, backpropagation asks, hey, how did the middle layer contribute to this mess? And then, how did the input layer shape that middle layer? It traces the chain of influence backward, one local relationship at a time. So every single weight gets a tiny, precisely measured correction. And incredibly, in modern AI, this backward whisper happens literally billions of times a second. Let's wrap all this up with Section 4, the continuous training loop. We've seen the forward movement, we've measured the mistake, and we've watched the backward flow of correction. Now we just tie all these individual steps together into a living, breathing routine. This is the training loop. It's the daily habit of the model. First, the forward attempt. The model tries to produce an answer. Second, measure loss. It compares its answer to the actual target. Third, backward guidance. Backpropagation traces the responsibility for the error. And fourth, adjust parameters. It takes a small step downhill. Then, it just repeats. Training is this patient, continuous cycle of improvement that gradually builds intelligence. It isn't one magic light bulb moment. It is a highly measured, repetitive routine. And honestly, if you take the time to walk through this book slowly, you earn a really profound kind of builder's confidence. You're going to understand a neuron's decision without having to pretend it's a literal human brain. You will see exactly how layers reshape signals. You will entirely demystify concepts like loss and gradients. You'll be able to mentally trace the chain of backpropagation. You will think clearly from second principles. And that means you will look at deep learning code not as some terrifying black box, but as a visible, totally understandable sequence of moves. As we close the notebook today, I want to leave you with one final, really reflective truth. A trained model doesn't just sit in a vacuum. It meets real inputs, real people react to it, builders observe those reactions, new examples return to the system. Deep learning is absolutely not just mathematics inside a model. It is a continuous, never-ending loop between a model and a constantly changing world. Understanding how that loop works inside the machine empowers you to guide it responsibly outside the machine. So tell me, what loops are you observing in the systems around you today?